Hey, I'm Larry the Learner, and what I want to do is get into quantum computing. And to get into quantum computing, I have to talk about the qubit, not the qubit, like they used to measure distance, but the qubit, Qubit. That is going to be our smallest information quantity in the quantum computer. That's the whole deal. Well, what was the smallest quantity of information in the traditional computer? It was a bit. And how did we store the bit? We stored the bit with a transistor, either a transistor logic system or a CMOS system. Electronics. Why are we talking about electronics? Well, guess what? You need electronics for a computer, even a quantum computer. So there are the traditional circuits and so on that go with a quantum computer, but it's all driven by this qubit, and the qubits are really expensive to make. So we want to understand the qubit. We can't actually look at one because I don't have that kind of resources to do that. So let's get started with this thing. All right, are you ready for circuits? This circuit is going to show us about a bit. And if we want to think of this as a 1-bit memory device, we can. The Q value shows us what the value of the data is. It just happens because of this circuit, this other one's going to be the opposite level. If this is a 1, then this is a 0. If this is a 0, then this is a 1. So let's follow through this. A transistor here has a base, an emitter, and a collector. If the base has a high voltage applied to it, then it turns on the transistor, and the collector goes to close to a 0 volts, or about 0.2 volts. If the transistor is off, meaning there's no current flowing between the base and the emitter, it's really a current controlled device, then this is off, and this resistor, which is often called a pull-up resistor, will bring it to a 1. Now, let's say that this transistor and this transistor didn't exist, and I just turn it on. Well, if I just turn it on, these two transistors are going to fight each other. One is going to want to turn on, and it will force the other one to turn off, or vice versa. So let me just say, by chance, this one is a 0. So if this is a 0, and we first turn it on, it's kind of a race condition, who gets there first. Let's say this one is a slow boat. So it's still low after I apply the voltage. Well, this one gets to the 1 value before this one does, so this 1 turns this transistor on and keeps this thing low. Whereas if this thing is low here, then it keeps this transistor off and keeps this one on. Now, what would we need to do to flip them around? Well, let's see. This is a 0, and if this is a 1, if I want to flip them around, all I have to do is turn this transistor on, and then it'll bring this low, and then the two will flip places, and we'll have a 1. So we've got this flip-flop circuit. And what do? We've got 4 transistors to store a value of 1. And these S and these are going to be used to flip the bits around. So you can think of this as the data coming in and this as the storage of a 1. So this is going to be our 1-bit memory device. Now, later on, we're going to compare this to a qubit and see what kind of storage it has. We will find that it's going to be not a 1, not a 0, but it's kind of like a coin. This is what you'll see other YouTube videos like this. A qubit is like a spinning coin where you see the heads and tails and heads and tails, heads and tails, and this is what superposition means. Well, I'm not so sure that's exactly right, but let's just live with that idea for now, that it would be going 1 0 1 0 1 0 1 0 1 0 1 0 1 0 all the time, and somehow that seems like a ridiculous thing. And how could a qubit store memory or any kind of information? And that's what we want to find out. I hope this part you can kind of fix in your head and rationalize this as a flip-flop with one of these a 1, one of these a 0, or vice versa, and they can be flipped by either of these two inputs. Qubit. Who wants to know about a qubit? Well, if you don't want to know about a qubit, then forget about quantum computing. Anyway, I described a bit. That 1-bit memory that we did with flip-flops. Now I'm going to talk about a qubit that is weird, to say the least. And some of it might refer back to videos I did on quantum mechanics when we talked about the essence of that, and in my playlist In Search of a Quark. With that said, let me proceed here to the concepts that I pulled out of artificial intelligence. Artificial intelligence was better than my intelligence, so I'm going to go ahead and use it. Anyway, here's the write-up. The physics of a qubit. Superposition. Superposition means that it could be here or here. Here or here, here or here, here or here, here or here. And we're going to say that there are 2 locations. Let's say we have a box, and that box we divide into half. And we say that the particle can be in one half of the box or the other half of the box. Now, if that's true, then the probability that it will be in either this side or this side is going to be, what, 0? No, there's a 1 probability. The probability is going to be 1. It's going to be one of those 2 sides. But here's the problem is, the probability that it's one or the other is not going to be 100%. So, here's what we have is this, ooh, doesn't this look like physics stuff? Greek letters, psi, alpha, beta. Then we have these things. And you know what those are? Those are ket brackets from quantum mechanics, because the pieces that we're using to represent the bits is not a transistor state on or off, but it's where a particular particle is in the quantum mechanical realm. So, if that makes any sense, I'm surprised. I'm surprised it makes sense to you. But anyway, if you're confused, then you're probably listening. Anyway, that's the probability function that's set up here. And let's see, because that's the probability. Okay, anyway, that's the idea of superposition. Now, did I explain it? No, all I did is just barely touch on the surface, because that superposition is probably a whole video in itself. Now let's go on to measurement. When you measure a qubit, in other words, you actually go in there and say, I'm going to take a measurement of it, all of a sudden it's either a 1 or a 0. So as soon as you measure it, you got absolute certainty of where it is. Until you measure it, it could be that's the probability thing. So let me scroll down here, move this stuff up. When you measure, okay, the probabilities are set by alpha squared and beta squared. And those lines around it mean the absolute value. So the probabilities is not 1/2 and 1/2. It's more complicated in that. And that's why I've got to keep moving here. Okay, physical. What's the physical realization? Here's the possibilities. Here's some of the makeup of a qubit method, a physical qubit. A qubit is not just a couple or a sprinkling of transistors. I think we did with the RS flip-flop. It took us 4 transistors and some resistors and so on to set that up. Here, the superconducting circuits can be the quantum mechanical qubit. Think of them as oscillators tuned by currents and magnetic fields. Does that explain it? No, that doesn't explain it. That says we need a whole video on what the superconducting circuits are and how those can be a qubit. Now, trapped ions. You know what an ion is? That's an atom where the positive and negative charges are not balanced. It's either a negative or a positive ion, and guess what? An ion, that means it's got a charge, so it's going to move in response to a charged field. So they can be manipulated with electric fields. And they also say something with lasers. Lasers? Electric fields? I don't know. It gets pretty weird, doesn't it? Let me scroll up here and get some more stuff here. Photons. Okay, have you heard about light polarization? Light can either be in this direction or this direction when it you have polarizing lenses for sunglasses that help you filter out the light. But anyway, those polarization states can be the different 1 and 0 probabilities that we come up with. Now, here's one that I absolutely don't understand, and I would have to go back to artificial intelligence to help me out and learn about this. This is called entanglement. It says it gets mind bending. Well, my mind hasn't even got in there to get bent yet. Okay, 2 qubits can become entangled, meaning, 1 qubit, I always have trouble with the screen. One qubit can affect the other qubit. 1 qubit can affect the other qubit. So that means that the state of one automatically forces the state of another. You want to know how weird it is? Here's this little statement here. Einstein called it spooky action at a distance. Spooky action at a distance. See, this stuff works. We can make measurements and we can make qubits, but the actual physical thing is a little bit hard to understand. And this last one is pretty easy to figure out. Coherence. They need to stay in superposition or entanglement long enough to compute. Well, that's kind of an easy phrase. Let me highlight that so that we can kind of emphasize it and say it again. So that they can compute. That's why it's so sensitive. A little something touches it and all of a sudden the entanglement or the superposition or none of those factors take effect, and then it's not one state or another, and then it's not a quantum bit, a qubit. So, but noise, temperature, electromagnetic interference can disrupt them. Okay, quick review. Quick, because we're running out of gas, and you're probably saying, I'm not going to watch this video, it's getting really boring. Superposition, physical realization, entanglement, coherence. Mainly the weird concepts are superposition, entanglement, and coherence. Here, I couldn't even remember them. Superposition, entanglement, and coherence.